You have to pay attention to this. Okay. Right. Next. So we have done with AX. Now we are going to focus to AY. Okay. So if we were to look at AY now, right? Now AY is perpendicular. So I'm going to sketch this in orange. Okay. AY is happen to be what? Perpendicular to the what? Centroid. When this is the case, right? When this is the case, the moment is relative to the what? Is relative to where the position of the elements are. Okay, do not worry, I'll write this down. Okay, so when the force component, okay, when the force component is perpendicular okay, perpendicular to the centroid, right? The perpendicular distance is to the position of the element. Okay, so for this case, right, AY, now we're going to focus on AY. AY, right, we already declared it's perpendicular, right, to the centroid of interest. So the perpendicular distance is 8 plus 8. Okay, it is still going in moment in the z direction. Okay, so we are going to now look at AY will also generate a moment about the z-axis. Okay, so we're going to declare anti-clockwise that's positive. So moment about z will be equal to what? Will be equal to AY multiplied by 60. So it's 3.441. Okay, so 3.441. So positive 3.441 times 10 to the power 3 multiplied by the distance of 8 plus 8. So this will be equal to 3.441 power 3 times by 16 will be equal to 55.056. Or 55.056 pound each. Okay, there you go. Okay, so the important thing is this. Okay, okay, so the important thing is when the first component is perpendicular, the perpendicular distance is to the position of the what? Of the element. Okay, so like the one in green, right? AY is perpendicular to the center of interest, and then the perpendicular distance is to the element, which is 8 plus 8. And then when we have AX, now AX is parallel to the what? Parallel to the centroid, right? So you take to the distance to the perpendicular distance is to the centroid. Easy to remember. So once this is done, okay, the moment or mz, so whatever that's anti-clockwise, you take it positive. So therefore, mz will be equal to what? Will be equal to minus 39320. Okay, minus 39320, and then plus 55056. Okay, so this will be equal to 39320 minus 39320 plus 55056. The moment will be 18 Okay, wait. 39 minus 39320 plus y55056 is equal to 15.763 positive 15.736, right? Times 10 to the power 3 inch, and it's going in the anti-clockwise direction. Okay, so going anti-clockwise direction, we know that this is anti-clockwise, right? So this will up the moment about Z. So this will be going on compression, and this will be going on tensile. Okay. Now, this is one way of doing this. I'm going to show you another way of doing it, and the answer will be the same. Okay, I'm going to show you another way of doing it, and as I said, the answer will be the same. Okay, and I want you to be comfortable with both methods. Okay, so this is the other method number 2. So we know that we have AY over here, AX over here, and we are aware that we have an AY over here, right? So over here, we know that AX, I'm not going to recalculate AX. We did earlier, AX is equal to 4.915. Okay, 4.915 times 10 to the power 3 pounds. And AY, we have calculated is 3.441. Okay, 3.441. Okay. Now, another way of doing it is by using static analysis. Okay. So what we know is if we are going to focus at point B. Okay, we're going to focus at point B, and we're going to focus at AX. Okay. So we know that over here we have a BY, right? And because the structure is on the left hand side that is empty. Okay, so this side is hollow, right? You can see this side. I'm going to shade in. I'm going to highlight in yellow. Okay, so this side is hollow, right? We always assume moment at point B is in this direction. Okay, this is assumed based on positive shear and positive bending moment. More based on positive bending moment. More based on positive bending moment. Okay. And then we know by looking at AY, we know that BY will be coming down. We know that. Okay. We know that BY will be. So what we are doing now is we are going to find the reaction. Let me see, can we use this technique for this example? Unfortunately, I'll tell you why we cannot use this technique, because we don't know, right? We don't know the distance from here to here. If we don't know this distance, then the only way to solve this problem is using this method, unfortunately. Okay, I do apologize. I thought we know the distance, but we don't know. Okay, so later on, I'll show you method number 2 when we have that distance. Okay, I just realized that I don't know this distance. When we don't know this distance, that's where the problem comes. Okay, fine. Okay, so we're going to try method 2 in let me see, method 2. Can I show you in another example? Okay, method 2 will be shown in example 2. Okay. As I said, why we cannot use method number 2 over here? We don't know this distance. Unfortunately, it's not given to us. Okay. Now, coming back to what we have discovered already. So by looking at this structure now, okay, by looking at this structure now, I'm going to copy this diagram over here. Right. So what we already know is we know, so if this is our X, this is our Y, this is rotation about Z. We are aware that we have a moment about Z, which is equal to what we have calculated that, which is equal to 15.736. Okay, 15.736 times 10 power 3 pound inches. And then we are aware that we have a load down here, and this corresponds to our AX, and that value over there is equal to 4.915. Okay, 4.915 times 10 to the power 3 pounds. Okay, 4.915. Let me check. 4.915. Yes. Okay. So from here, if we were to look at our formula, we know we have stress X is equal to Px over A, or plus minus. Okay. And then we have plus minus My over Iyy multiplied by Z plus minus Mz over Izz multiplied by Y. So for the fact that we only have Mz, this is equal to 0. So in the end, we only need to use plus minus Px over A, okay, plus minus Mz over Izz multiplied by Y. So from here, we know that our loading is classified as eccentric, symmetrical, bending. Okay. So cross-sectional area, straightforward. So the area is equal to so if we look at over here, right? So I think I'm just going to copy the image that we've drawn earlier. This one over here. Right. So that is the image that one. So the cross-sectional area is 3 inches, or is equal to 0.8 multiplied by 3 is equal to 2.4 inches squared. So the next thing that we have to find is our IZZ. ZZ is our interest, axis of interest. Therefore, this is our width. And over here, this is our depth. So the width is equal to 0.8. The depth is 3 cubed over 12. So 0.8 times by 3 power 3 divided by 12 is equal to 1.8 inches to the power 4. Okay, again, I try 0.8 times by 3 power 3 divided by 12 is 1.8. Okay, so now we are going to look at, before we go there, or look at, we know that based on MZ, this is compression. And down here is our what? Tensile. Okay, so let's look at A first. Okay, so moment at Z, or stress X, for element A. So this will be equal to P over A, Px over A. So this arrow is pulling away from A, B, and C, so it's tensile. Okay, so positive 4.915 times 10 to the power 3. And then we are going to divide by our cross-sectional area, 2.4, right? And then the next thing is mz over izz multiplied by y, and A is under compression, so it's minus. Okay, minus mz, which is 15.736 times 10 to the power 3. The y distance over here is 1.5 relative to the centroid, and then we divide by 1.8. Okay, divide this by 1.8, so we will have 4.915 power 3 divided by 2.4 is equal to 2.048 times 10 to the power 3 minus 15.73